Univariate analysis is the simplest way of understanding the data.
Let's start creating the histogram with the cone bins. Remember that if you want to implement these scripts in your QGIS, just watch the video number 5 of the first geostatistics course. Then to do that one, we are going to go here to R, open the scripts that we already created. Is this one over here, and it's going to be the number 6. Then we have to go down, and number 6 is this one. Double click to open. Then the data set is going to be this one. Is the only vector layer that we have. Then it's loaded automatically. The parameter is going to be the groundwater elevation. The X is going to be the groundwater elevation in meters. The Y is going to be the number of samples. Title of the graph is going to be histogram. Subtitle is going to be raw data. And now I'm going to add all the labels, but I'm going to pass the video faster. To put the range, the minimum and the maximum, we are going to go to the attribute table, open the attribute table, and then we are going to click on the top of the column here at the groundwater, and in that way we can change from the minimum to the maximum when you are pressing the top of the column. Then the minimum is this one. Then we are going to select the content, and we are going to paste over here. For the minimum is this value, but we are going to keep just 3 decimals. Then I'm going to remove all these ones, and I'm going to do the same for the maximum. Then go here to the attribute table, select the maximum, copy and paste here for the maximum. Paste, and I'm going to leave just 3 decimals. Delete. Then with the calculator, we are going to make the difference. Calculator, and it's going to be this number. Copy, paste over here, less 1000. Sorry, I make a mistake. Less 312.108, and this one is the difference. And then we can divide this number between 10. That is going to be the number of bins. That's equal to this number. Then we can copy this value, copy and paste here, and that one is going to be the number of intervals for this histogram. Paste. Remember, I decided to put 10 bins because when you are making the root square of the total number of samples we have here, the total number is 85. That value is going to be 9 point something. We can make that one. Let me show you. Then it's going to be 85 root square. As this value is approximately 10, that's the number of bins I'm going to add in my histogram. You know, in order to know how many bins you can add to the histogram, you can do the root square of the number of samples, and that's what I did. Now we can run the script. And double click to open. Let's go to make this screen bigger. Well, we can say that this histogram doesn't look normally distributed. Even looks like there are 2 different distributions, this one and this one. It is known as a bimodal distribution, but as these values are related with the groundwater elevation, I'm not going to consider that these 2 different type of distributions, this one and this one, it comes from different events. It doesn't make any sense here, right? Because from my point of view, all the piezometers are from the same hydrogeological unit. And also, all the measurements of the groundwater elevation were taken at the same day. then we don't have, for example, wells that are screened in a different hydrogeological unit, right? That can make a different distribution of the data. I'm assuming that all the wells are from the same aquifer and all the measurements were taken at the same day, and that's very important. In order to know if the data is normally distributed, we can run a couple of scripts that we created at the lesson number 9 of the first geostatistics course. These scripts are the Shapiro wheel test and also the kolmogorov-smirlov test. In this case, as the number of samples is more than 50, we are going to use the kolmogorov-smirlov test, and that script is the number 18. And double click to open, and as you can see is the Lily test. It's an improvement of the original version. Then here we have to select the layer that is loaded by default because it's the only vector layer that we have here. And then the parameter is going to be the groundwater elevation. Then we can run the script. As the p-value is smaller than 0.05, we can conclude that the data is not normally distributed. It's not following a Gaussian distribution. And remember that we want to have a Gaussian distribution or closer as possible to Gaussian distribution in order to have a better representation of the experimental semivariogram. Remember that the function for the experimental semivariogram, it's not parametric, and then it is not necessary the data to be normally distributed, right? But as closer is to the normality, better is going to be the interpretation of the experimental semivariogram. And consequently, better is going to be the model that we can fit on the data. Now, let's go to see if we can make some transformation on the data to improve the distribution, to have something that is closer to the normal distribution. Then to do that one, we are going to go to QGIS here. Then we can close this one. Also, we can close this one. But first, I would like to see the histogram with the box plot to see what is located the mean value and the median. Remember that the script that we are going to use now, it's part of the lesson 6 of the first geostatistics course. Then if you want to implement that script on your QGIS, just watch that lesson. The script is the number 13. Double click to open. Then the data, the layer is going to be the data set. The parameter is going to be the groundwater. The label X is going to be the same as before for the histogram. Then it's going to be X is going to be the groundwater elevation in meters. Y is going to be the number of samples. Title of the graph is going to be histogram plus box plot. Subtitle is going to be raw data. And the range is going to be the same as before. I'm going to add all this information, but I'm going to pass the video faster. Now we can run the script. Double click to open, and let's go to make this screen bigger. As you can see, this histogram is the same as this one, but now we added the box plot over here. As you can see, the box, this box is not at the middle of the graph. Also, as you can see, the mean value, that is the solid red line, it's not the same as the mean. The mean is the dashed black line, and these two lines are separated. And also that is indicating that the data is not normally distributed. If we have a normal distribution, these two values are going to be together. In this case, what happened, these high values over here are pushing the mean value, the red line, to this section of the graph. Because of that, we can say that the mean value of the data set is not representative of the data, because we have these high values over here that are pushing the mean value, but it's just 3 values when the majority of the values are located in this area. Then this type of thing is impacting a lot on the experimental semivariogram, and we want to avoid this type of issues. Then let's go to start with the log 10 transformation. To do that one, we are going to open the attribute table. Let's go to make this screen bigger, then press the pencil to edit this table. Then we are going to go here to this icon over here, open field calculator. And we are going to create a new field name that is going to be log 10. It means the logarithmic with base 10. Then this one is going to be decimal number, and with precision 3 decimal is good. Then we are going to go to math here, then select log 10, double click to open, and now we can minimize this one and open field and values, and here select the column for the groundwater. Double click to select, then close the parentheses, and then we can run this one. And now it's created a new column with a log 10 for the groundwater. Now let's go to do another transformation. In this case, we can do the root square. And here again, we are going to take 3 decimals. Is good, decimal real number. And again, we can go to math, select the root square, square root, sorry. And it's going to be the field and values, this one, and select again the groundwater, and we can close the parentheses, press OK. And also another type of transformation could be the inverse transformation. Then again, open the field calculator. In this case, it's going to be the inverse. And we are going to add here decimal numbers. As the number in this case is going to be very small, we can put, for example, 6 decimals in this case. And here the formula is going to be 1 divided by the field that is going to be the groundwater. Double click to open and OK. Let's go to verify with 6 decimals is good and looks pretty good. And then we can close the edition to save all the changes. Save. And now we can do the histograms of this type of transformations. Okay. Then the first is going to be the log 10. Then we can run this one again, but now these values are going to change. Then open the attribute table and see the minimum and maximum for the log 10 transformation. Then for this one, copy this value. That one is going to be the minimum. Paste over here. Then the maximum. The maximum is this one. Copy. And paste over here. Now we are going to make the difference with the calculator. Then go here, calculator, double click to open, then select this number, copy, and let's go to make the difference. Paste here, less this number, 2.494 equal, and this number divided by 10 because that's the number of bins, equal, then copy this value and paste over here. Paste, and this one is going to be the log 10 transformation. Now let's go to run this script. Log 10 for the groundwater also. And run. Double click to open. And I know what is the problem here. The problem is I didn't select here the log 10. Run. Double click to open. And we can make this screen bigger. As you can see, doesn't look like that we improve the distribution of the data. If we compare, not this one, if we compare with the original one, there is not too much differences. Looks like even the same. That's true that the mean value and the median value, they are closer to the middle, also the box, but the distribution of the data, it's not improving. Even we can do again the kolmogorov-smirlov test. Let me check over here. Then in this case it's going to be for this parameter, the log 10. And if we run this script, we are going to see that the data, it's again not normally distributed because the value is smaller than 0.05. Looks there is an improvement, but still not good. Now let's go to see with the square root. Then I'm going to close this one, I'm going to close this one, going to select this one here. Then it's going to be the square root here, square root, then this one, square root, and let's go to change these values. Here is going to be this one, the smaller is this one, copy, paste over here, the maximum is this one, copy, paste over here. Let's go to make the difference with the calculator. Then going to paste the maximum here, minus this value over here, 17.667 equal divided by 10. That is going to be the bin. Then I'm going to copy this value, copy and paste over here. Paste, everything is okay. A square root transformation, a square root for the groundwater elevation, and this value is good. Then run this script. And double click to open. Let's go to make this one bigger. And again, as you can see, we don't have an improvement, it's still the same. We can run also the kolmogorov-smirlov test, but for the root square here, run, and the value is smaller than 0.05. Again, we don't have normal distribution. And in both cases, for the square root and also for the log 10, we still having the bimodal in both cases, right? Now let's go to see the last one. That is going to be the inverse transformation. Then go here, select this one, then it's going to be here the inverse. We can add here inverse, or we can add here 1 divided by the groundwater. Here we can say inverse transformation. And let's go to change that values here. Let me see what is the minimum. This one is the minimum. Copy, paste over here. Then let's go to select the maximum. This value, copy, paste over here, paste, and with the calculator we can make the difference. Going to paste here the maximum, minus 0.05. 0, 0, 0, 9.9, and then equal, and that one divided by 10. Then I'm going to copy this number, copy and paste over here. Paste, and let's see the histogram. Then double click to open here, and let's go to make this screen bigger. With this transformation, the mean value and the median, they are pretty close, but the box is still not at the middle of the graph, and also looks like bimodal, two different distributions. But let's go to see what kolmogorov-smirlov can say. Then let's go to select the inverse and run the script. In this case, as you can see, the p-value is smaller than 0.05. Then we can say that the data is not normally distributed. Then, as a conclusion for the univariate analysis, we can say that we cannot improve the data distribution because we did 3 different type of data transformation and no one of them improved the distribution. But it doesn't mean that we cannot use this data for making the experimental semivariogram and then fit the model, you know, because as I said previously, we can do the experimental semivariogram even when the data is not normally distributed. But the best scenario is when the data is normally distributed. However, in this case, I'm not worried about the data distribution because as we are going to see now in the bivariate analysis, the data has trend, and then we are not going to work with this data. We are going to work with the residuals of this data, and the residuals are going to be a different distribution, right? Then that's the important thing for this specific case. But the conclusion, the things that you can get, that even when the data transformation doesn't work and doesn't improve the distribution of your data, you can still using that data. But your results are not going to be as good as when the data is normally distributed. Maybe you can think that we can use a different type of transformation, something more sophisticated like Bose-Cox, for example, but also in this case, I tried that transformation, but it doesn't work. I didn't show you here because it's not part of the scope of this course. And also, for example, you can do a normal score transformation where you force the data to follow a normal distribution, but that case is a little bit more complex. You know, it implies a lot of transformation of the data. Then you are using a simple Kriging, you know, that type of transformation. It's a little bit more complex and it's not part of this course. But the conclusion again is just to know that if the data is not following a normal distribution, you have to be very careful when you are doing the experimental semivariogram and when you are fitting the model, you know, but it doesn't mean that you cannot use that data. You can use that data, but just be careful, right? Now let's go to move on to the bivariate analysis. That is going to be the interesting part of this second lesson.